Record. So, hello everyone, and I'm very happy to host this fourth talk of the series number 6 of the EDT Engineer Digital Twin seminar. And today we are happy to have this talk. So, just quick word on some events related to digital twins, as we have advertised them in the previous talk. So we have like few events, the workshop on model-driven engineering digital twins that will be held at Models Conference. So the deadline is July 7th. Feel free to have it in mind so you can submit some interesting work there. There's another workshop as well on digital twins for business process. The deadline is rather near by the end of May, but again, it's also nice, could be a nice event for our audience to think of. So today we are very honored to have a talk done by Fredrik Nordfeldth and Joakim Mörk from Algoryx. I will just give a quick word in the next slide. Just to remind you that, as has been tradition, we have 5 talks. So we'll still have one talk scheduled in 2 weeks from now from Pierre Jean-Rivière from Airbus. And we will end the series after 2 weeks after that with a panel discussion, as we have been doing this in the EDT seminar. So today talk is going to be given by two speakers. Thank you for accepting our invitation. Fredrik Nordfeldth, who is a principal R&D engineer at Algoryx. He has more than 15 years experience in engineering of simulations and building simulators. Among going projects, he's involved in the IM European Horizon project and the BRIC, which is to define language for defining extendable schema. Our second speaker is Joakim Mörk, who's also working at Algoryx. He's senior R&D engineering there. Both have a master diploma from UMA University. And Joakim also is currently project managing a lot of projects around physics-aware heavy machinery, primarily in the mining sector. And today they'll be talking about the physics-aware of digital twins. So without any further ado, thank you again for accepting our invitation, and the floor is yours for sharing your slides and starting your presentation.
So thank you for inviting us, and thank you for the introduction.
Yeah, thank you very much.
Okay. Yeah, last time I was sharing here we go. I think. Can you see Algoryx on the screen?
Yes, I can see the slides, Algoryx.
Perfect. I didn't see them myself, but now I see them. Thanks. Okay, so I'll start. I'm Fredrik from Algoryx, and with me I have Joakim. So I'll start just introducing Algoryx. We're a spin-off from UMA University, founded in 2007. So I've been there a long time. We're about 35 people today, and our 4 founders here is in the below picture. We're still active in the company. And here are bios that we sent to you. I'll skip those. We just got introduced nicely. And I'll just leave it over to Joakim.
Yes, thank you, Fredrik. So digital twin definition is the first thing we'll start with, but there are a number of things. So in proper order, I'll first present the contents aside from that, so you can revisit them as the talk goes along. So first, me on digital twin definition, then ADX dynamics will be presented by Fredrik, and BRIC will also be presented by Fredrik. And last, I'll come back and present a case study, a project I'm currently working on with the mining industry. Digital twin definition, an interesting thing I looked a lot on this channel, because there have been a lot of talks on this topic. For instance, there was an article, I can't remember if I found it in the channel or Googled it, but this is one definition of digital twins. As people, followers of this community has observed, there are a number of ways to use the term. This is a definition I liked because it encapsulates how we use this term. Digital twin, set of models of the system, a set of digital shadows, and it's a set of services to use the data with respect to the original system. And that's kind of the theoretical model, right? So set of models of the system is the physical twin in the terminology that we like here. And the digital twin is the digital shadow then. Both these systems have typically hardware parts and software parts. These images show how the setup usually looks like in our work. There is some kind of hardware or like a heavy machine, could be other things, but it's the representative of what we work with. And the hardware has software, and both the physical and the digital twin have those systems, and then they interact. There's data going from the physical twin, and there's control going back to the from the digital twin to the physical twin. This is also from theoretical stuff we've been looking at, and it's kind of, if we don't have all these four parts, the two twins and data and control, then it's kind of, well, parts of a digital twin. But this is generally one test we use to see, are we using this kind of workflow? It's a workflow we sell to our customers, so it's useful to have a definition. And on the next slide, I'll just say some words on kinematics versus dynamics. Because it's thank you, Fredrik. It's useful to look at just the right amount of stuff, right? Kinematics is a traditional way of controlling robots. For instance, robots. You have angles and positions of the different parts of the robot. A really stiff system, typically. An industrial robot doing welding in a car factory perhaps is very stiff, and the path planning can be parameterized, since all the positions can be, since the position of the end effector can be known from angles and position. Scenarios are well defined. You can use inverse kinematics to know where the robot is going. And with dynamics, we also have, next click, Fredrik, we have the forces, the inertia, and the energy is known apart from the angles and positions. The path planning can be reactive. For instance, if some heavy load is placed on the robot, you can calculate and work with the energy related to that. Reactive scenarios, reactive to collisions mainly, that's one of the big ones. We can also work with deformable objects and inverse dynamics, which is a topic I'd like to have said more about, but this isn't for this talk. So this is a distinction we often use. Next, we have a slide packed with information. This is a PLM slide, product life cycle management, is one way of reading that acronym. So the product starts its life as an idea, then it works its way down through the decomposition and definition phase, implementation, development process. Then the product actually gets created through testing and validation. And then on the top right, we have operation maintenance, changes, upgrades, retirement, replacement. This is the product life cycle. And a digital twin can be used in all of these parts, really. It's a thing that can accompany a product on its way through life. Through virtual prototyping is on the top left. Then we have other bubbles pointing to different parts of the V shape here. But you can always, actually where the bubbles point to is kind of irrelevant, since most things can be at many stages on the V here. The interesting thing is that the same digital twin can be reused on different stages of the product life cycle. This is a lot of information, I guess. Virtual prototyping is one of the things where digital twin technology in engineering is kind of mature, but training, certification, and testing are also parts that are getting bigger and bigger, at least from our perspective. And if you look at the next click, we can see like it's made a small arrow there. Digital twins can be offline and online, right? there can be a simulation of the digital system that happens kind of discrete time, not real time. So you make a simulation at the concept level, and then you test things out, and then you go back and testing on the physical, and you go back and forth between the digital. But it doesn't have to be in real time. But when you go to a digital twin modeling something that's happening right now, and it's an online simulation. Yes, next slide. Next, yeah, I'm sorry for having all of these intense packed slides here, but these are a few areas. We try to divide digital twin as a solution into. We have to define the machine in some way, author the physics. The CAD is of course what defines the product often, but we also have to define the physics in order to use the physics-aware simulator. We have to define environments in which to use the machine. A heavy equipment often use rough terrain and such. Sensors and perception needs to be simulated, dynamic scenarios, simulation services. Maybe you don't want to run anything on one computer. There needs to be expertise and feedback through control and ML training, test and certifications, monitoring and logging. These are all parts of digital twin as a solution. And once again, classically, simulations can be just a small part of this. So in order to tie everything together, we've been trying to define a modeling language that can follow the digital twin along between these kind of, this is kind of opening up from just the machine simulation. Yes, so next slide.
Okay, I'll take over then. So I will start then by explaining our main product, which I have to mention it requires then a commercial license. So our main product is a physics engine. So we are really fast and stable and robust and accurate. And we are working the non-smooth domain. So we handle impacts in real time, and we can handle drive friction as well. And our product is based on the Spook method, which is presented in Ghosts and Machines, which is written by Claude Lacoussière, who is one of our founders. And just to mention, so that we can guarantee stability by setting a damping time, which will then make our equations to be satisfied, and we get good matrices to solve. And just to make an example here, what type of simulations do our customers do? So this is actually our first customer who is doing a marine anchor handling simulator. And my first few years was a lot about modeling these wires that you see, so that we have full scenarios with anchor handling. They have a kilometer-long wires that need accurate measurement of tension. They will roll these things on drums, and they still need these detailed parts where we have anchors and chains that interact with each other. And their product is then a training simulator, as you see down in the down right picture. Other things that we could say that we do, that earth moving operations, and we can handle hydrodynamics with waves and wind. And also like wire simulators, you can see a small video there. And then the middle video, we have cables and cable damage, which is one of the examples that Joakim will show you later. And we can also handle large millions of particles in large granular systems. And then these modules are then accessible today through like coding interfaces, mainly used in C#, C++, and Python. We also have integrations in Unity and Unreal. However, then to the right now, you see a list of our customers, and they integrate this into their system. They adopt our product and integrate it, and they have a lot of requirements that they usually have to do on their side. So usually they do something autonomous. They have a control system in the loop in their real product, and they want a digital twin that they either want to use for machine learning or developing their control systems or doing training simulators. And so control system integration, they always need to do. They want real world equivalent performance. So for example, these wires need to have accurate tension measurements. They usually have CAD representations of their products. They want the CAD more or less automatically reflected into simulation, which is not usually a thing. So in the green squares in this figure here shows that they start from CAD, then they have to do this long process to simplify the CAD. They will need to add some physical properties to this model. They have to model a scenario somehow, maybe in code, maybe somewhere else. They need to add a lot of logics in scripts, and then they can put this into the simulation to do what they want. They also want this in variable configuration. So the CAD might be in one configuration, but they want a different setting somewhere or slightly different product to simulate. And then there's a lot of work to redo this from the beginning. So this is something we've been working on, how to make this more general. So they also need this single source of truth for the simulation model, so that it's not like, oh, did you remember which file we did this part of the thing, and then they email the simulation models to each other, which has happened, and that's something they want to avoid, but it happens. So we try to solve these problems for them. So we need somewhere to define this physics-aware digital twin, but where should we define it? And some of our users, they make their own formats and so on. And we've seen this throughout the years, and we want to come with something that solves a lot of their problems. We have tried to use some XML-based formats, but URDF is the Universal Robot Description format, but it's not enough to meet all simulation models that I mean, a wire is not described there. There are a lot of things that doesn't fit in these formats. Then we have been looking into the universal scene description format developed by Pixar, which has bindings to C++ code, that it has a layer system where you can really have these definitions on top of definitions, but it's mainly used for graphics. The physics layer is not mature enough, and there's, according to me, one thing missing with expressions, where we need variables in these mathematical expressions to describe our models. So that wasn't good enough for us either. But we looked into Modelica, and Modelica gives us these expressions, but it's not, we couldn't find a good fit for these real-time simulations with bindings to control systems and so. So we had to develop something ourselves, and this has been ongoing for a couple of years. So Brick is then, to be clear, so Brick is an open modeling language. Then we use Brick to define the Brick physics format. So Brick could be used for other things than physics, of course, but later on now I will show you how we use Brick then and describe the physics format and its features. And using this format, we can then bind it to our API in the physics, EDX Dynamics, and then we have the EDX Brick runtime. So then I would say that Brick would then address these parts of the customer simulation process, where they would then maybe get values from CAD and describe the physical properties of the models and describe scenarios, and they could eliminate a lot of logic that could then be living in the digital twin representation in Brick. And then AJX Brick runtime would then load this model, and they can immediately do their work. So just quickly, Brick, I would say, is a declarative language. It has a custom syntax which is human readable, writable, strictly typed, object-oriented constructs it uses, and you can reuse models. It supports inheritance. You have type specialization and these mathematical expressions and much more. And we'll go through a couple of features here. So it's one important thing is that it's self-describing. And here, the main reason is that we don't want customers to build their models in their code. We want to separate the model from the application. So here we have the shared domain, which represents all physics that we would like to simulate, more or less. And we want the model in this shared domain. And then we want to be able to load this to the APIs of different tools. So it shouldn't be bound to our product, of course. So we could load it with Bullet or physics or some other physics engine. That's one of the main purposes. But everybody does not want to model their product with multi-body, very general things. They want a domain-specific language. So Brick is built so that you can build domain-specific ontology and formats on top of other formats. So we would call it a bundle. So could be a Brick robot bundle that depend on the multi-body bundle. And in this way, we can bridge domains. So we can have a robot-specific ontology and a vehicle-specific ontology. And then with Brick, we mount, maybe we put a crane on a truck. And both are described with their specific domain-specific bundles, but then in the shared domain they can meet and then be executed in the tool. So there's one more level to this. So there are a lot of external resources that we would say are a better fit for specific model descriptions. So URDF, there are a lot of robots defining URDF. So we had to make a way for such formats to be referenced by Brick instead of you having to copy the data. And that's an important thing as well. I'll get back to that later. So, yeah. Okay, I didn't see. All right, so now I'm gonna try to explain here how you use Brick to model by composition and try to show how it's extendable and reusable by a simple example, as simple as I could make it. So these Brick bundles then, so say that I'm using the physics 3D Brick bundle, which has the representation of a rigid body. So it knows what the rigid body is in the multi-body domain. Then I want to declare a wheel. And then I say that the wheel has a radius attribute and a width attribute. And the wheel should also have a collision geometry. And then I add the collision geometry attribute, which then gets a type of a cylinder, which the physics 3D bundle knows about. And then I map these values from the wheel radius into the collision geometry. And the cylinder already have the notion of the radius and height. But then for the wheel, I call it width instead. I don't know if it makes sense. All right, so this is a wheel. And I can't instantiate this. It has two parameters that are not defined. But then I use Brick to say, now I want to define a simple wheel. And then I define these variables, and it's very compact and easy. And now this is instantiable. And let's say then I would like a more advanced wheel. Maybe I need to reflect the friction against the road somehow, then I define an advanced wheel which extends the simple wheel model. So now the advanced wheel model has both the radius and width parameter, but also the rubber roughness, which is something I just made up. Okay, and to create a vehicle, we need wheels and maybe we need a chassis. So then I define a chassis as well. And then I would like to create the vehicle. So a very simple vehicle would be you use the physics 3D bundle, have something which we call a system. The vehicle then is a system, and it has 5 attributes, 1 chassis and 4 wheels. Now I don't show you how I connect them together. That's a different thing, but imagine that we do that as well. So now we have a vehicle and there are 4 simple wheels. But then, as we said that we would like to evolve the physics-aware digital twin along the product life cycle, then you could imagine that you do some type specialization. So maybe you want an advanced vehicle in another stage. Then we use the keyword in BRIC, which is becomes, where we now in the advanced vehicle, we force 2 of the wheels to be of the type advanced wheel. Maybe it's not clear the purpose, but it is very powerful in how we model our representations. All right. The bundles I was talking about. So this is a quick overview of how it looks and could look. We could have we have a physics definition, which is a physics bundle. But then when we model 3D physics, we have something, a 3D physics bundle, which I just showed you snippets of. But then if we would like to define the vehicle bundle with vehicle domain-specific ontology, then we might want to define the drivetrain with a drivetrain-specific ontology. And the drivetrain might be a physics model that is just one-dimensional. We don't need 3D physics, but then we can have this dependency so that we utilize the ontology of both worlds, and we can model in the domain-specific with the domain-specific ontology, and we can give the user something that they recognize, but still everything propagates down to the multi-body shared domain, and then we can execute the simulation. Quickly about the BRIC infrastructure here. So we have C++ runtime bindings, I told you. And we have to go from text representation to a C++ runtime. And this is a quick view over the parser and how we do semantic analysis, and then how there's some parts, some bundles have C++ code that has to be executed on load, and some parts don't need that. You can build in logic into your models. And this also enables the evaluation of expressions, so that a variable could depend on several variables, and then you have the mathematical evaluation of equations. All right. So this solution, then BRIC plus AGX, gives us a great feature list, in my opinion. And here's a video. It's an old video, but it shows you how the CAD has been imported, and then we can assemble this with the BRIC definition. And this could then imagine that every part that's assembled is assembled by a constraint, and this constraint has variables, and these variables could actually have variable initial conditions. So you can configure this in any configuration that is available in reality. And then you can parallelize this and do simulations of your machine in various different initial configurations, for example. And this is what we did in one project where we developed an online web application for engineering design of loader cranes, where we could then, for example, change some values and then the crane just built itself and we could measure capacity of the crane and with its full working region. Other projects where we've been using Brick. Now this is actually the Brick language you just saw. That's something that's quite new. We were using YAML and just a subset of YAML, and it did make a lot of sense, but still there were some issues, and we decided to define this language ourselves. So the code you see now is the old Brick, and the new Brick would actually do the same thing in less half of the number of rows. So that's good. And this is the iTalk project where we had a Delta robot which have loops in the system. And I just show you how I can take one value and then which then propagates through the system and then initializes the model in a different initial state. And then you can simulate it as well. So there's some friction in this thing. So you can, this I think visualizes pretty well how Brick physics aware twin can be, the mechanics are assembled and useful. Let's move on. And you mentioned before that I was involved in the IAM project, and here we are also using the Brick AJX runtime. In this project, we are trying to make robots toss, grab, and box objects, and then we need this in simulation. So here we have the Panda robot, which is then an URDF file, which we take into Brick, and then we augment this. So the suction cup here on the suction gripper is not deformable, it's just a part of the URDF file, but then we can augment this and make it flexible. And then we add a vacuum system, and then we can have this simulation experience. And there are a lot of PhDs and postdocs and master's thesis students that work with this framework we're developing in IAM, which is using Brick, and it's also using something we call Click, which is an integration with control systems. And this is just one other work, and this is a thesis project by Stefan van der Palen, who's in Eindhoven, and he's doing verification, two things with his digital twin, I would say. He's doing both verification of sensor signal with physics. So he has a visual sensor that do this 3D estimation of where the boxes are. But then to verify this, he could initialize these sensor representations in simulation, and then he can verify in that simulation if it's accurate or not. And maybe the boxes will fall and he will require a new sensor request. And also then he can use the simulation in the control system and test before the control system is acting on the real system. So that's a work in progress, and that's one of many projects, but I will not go through them all. Another place where we are using Brick, the Brick runtime, and together with Unreal Engine, where we then integrate the Brick AJX runtime, and we visualize it in Unreal Engine. So then we have this result, and this is more or less the same thing, but we have nicer graphics. All right, so now I think I have showed you a lot of things that we can do and how we represent and we have imagined also that all our users in the future, and hopefully even it's more widely used than just our users, how we can represent physics models with Brick. All right, so let's move on. Now I move back to Joakim.
Thank you, Fredrik. Thank you for that very in-depth walkthrough of what lies behind our physics and what defines physics, how we define it technically. And I've been working more practical stuff, been using those systems, been using EDT dynamics, and been using Brick in order to do research and client projects. I've ended up doing mining industry things. Epiroc is one of our larger customers. And here I'm going to present a case study about digital twin simulation. This project is called Safe Remote Drilling Through Predictive Modeling of Hydraulic Hoses. We usually go with Hose Protect because it's about protecting the hoses on a drill rig, such as the one on the left. On the right, you can see a boom simulated with some of the hydraulic hoses normally present on the telescopic actuated booms on the boomer drill rig. And the Epiroc boomer is a complex machine interacting with itself and the environment. The question in this project is, how does the control system predict collisions with deformable hoses? Or rather, how should it predict collisions with the deformable hoses, detect and predict? Because traditionally the hoses are just placed there and hopefully they won't get in the way. The collisions with the hoses aren't really recorded or predicted at all. That's this project between Algoryx, Epiroc, and Örebro University. So in order to do this case, we've been spending a lot of time developing the model, or rather determining what to do with the model, because we have, of course, the cable simulation module in ADX that is used for the hose modeling, the hydraulic hose modeling. We'd looked into some variations on that topic, but ended up spending not all that much time on step one, but then choosing the parameters to simulate the hoses has been subject of a lot of research since, well, defining a box with a perfect box is easier than defining a hose, especially when a hose has different parameters, whether if it's pressurized or not. So there was some work done to use this setup from real life to record the motions in order to get the parameters to use in the mathematical physical model to perfectly simulate the hose in the latter part of the project. Step 3 would be to define the boom model and the variations on the boom and the hoses and specify that in Brick in order to do a large amount of testing for a large amount of hoses. That has been done at Algoryx, and while the work on determining the hose parameters is going on through the machine learning model at Örebro. Finally, to complete the project, test cases and metrics have to be defined in order to see if the predictive model would be of use. Next slide. Existing model is really not predicting hoses at all. Collision model for moving booms around in autonomous mode, or rather automatic mode, would be to have parametric boxes, forbidden zones, braided overlap. This ignores hoses, of course, limited number of boxes and output data. Still is a good model. The boomer machine can do automatic functions to a large degree. Here I'd like to just add some distinction between automatic and autonomous, at least in our usage of those words. There is large difference between those two terms, that in the automatic mode, there's very limited decision capabilities, while an autonomous system is able to make some kind of decisions based on complex data instead of just follow a path and the like. So we go instead to the new models and predictors that have been evaluated in this project. The machine learning model trained on the dynamics data from the simulation is one of the new models predictors that can be used for collisions and damage prediction on the hoses. And that is kind of the more established way of using this type of predictor, because an ML model can be differentiable, and it's the predictions will be faster with the differentiable model generally. There's also the online dynamic simulation that is more in line with the digital twin in the runtime scenario type of a digital twin model. Online dynamic simulation would be a control system that does its own dynamic simulation for relevant positions and angles of configurations of the machine in order to see what would happen. Since a great simulation of physics can see what will happen based on sensor data, there can be a lot of data taken from that simulation that can be used in the control system for the planning of drilling, movement of booms, and the like. Next, there is a small thing with sample articles from the project, mainly on the machine learning model. This project isn't complete. It's been overfunded. If I didn't mention that in the previous slide, there will be more articles published by Hushan Yang, the PhD student, and Johannes Stork and Todor Stoyanov. I think at least one more coming up. Finally, some quick demo of, some tests we did. These are just some quick tests of moving the boom around, looking at deformations, and if you can see it, there's a purple outline of a box following the hoses around. That's one quick and easy way to see where not to move the boom. If one would want to move the boom where the hoses don't collide with the floor, cliffs, other booms, and like. Right, I listed some summary there that the offline simulation that can be used. This is modeled. We've been using the integration with Unity, the AGX for Unity package. Using that, there can be virtual prototyping for placement of the hoses for like a static enhancement of the hose thing. But it can also be an online thing that's used in the control system in order to make projections of what's happening, which is what we call physics aware. The control system would, if using that method, be very much aware of the physics of itself. Yes.
All right. Thank you, summarizing it well, why we need it. All right, we are done. Thank you.
Thanks a lot for the presentation. So if anyone has question, feel free to either write it or just ask it directly. Yeah, so feel free to write it in the chat or just raise your hand and ask any question you want. I was thinking, so the distinction you, if I may ask a question, between the offline and the online